Hey, welcome to Image Production. This is Chapter 8 from the Faber and Johnston text, Essentials of Radiographic Physics and Imaging. To produce a radiographic image, X-ray photons must pass through tissue, which is your patient, and interact with an image receptor. The image receptor is the device that receives the radiation that leaves the patient, such as in a digital imaging system. Both the quantity and quality of the primary X-ray beam affects its interaction within the various tissues that make up the anatomic part that you will be X-raying. In addition, the composition of the anatomic tissues affects the X-ray beam interaction. The absorption characteristics of the anatomic part are determined by the composition, the thickness, the atomic number, and the tissue density of the part being examined. The radiation will exit the patient, and it's composed of varying energies, and it interacts with the image receptor to form the latent or invisible image. And then, of course, that becomes the manifest image. The process of image formation is a result of the differential absorption of the X-ray beam as it interacts with the anatomic tissue. The term differential is used because varying anatomic parts do not absorb the primary beam to the same degree. Anatomic parts composed of bone absorb more X-ray photons than parts filled with air. Differential absorption of the primary X-ray beam creates an image that structurally represents the anatomic area of interest. When we're looking at figure 8-1, you can see the primary X-ray photons coming down from the X-ray tube, and they go inside the patient. So they're passing through the patient. X-ray photons that are absorbed by the part. There's some in the middle of the patient's body that are absorbed. And then the other ones will become scatter radiation because they will not be absorbed by the patient's body and they will eject out, not hitting the image receptor and just scattering. So they're basically useless radiation. You see the image receptor underneath the patient. So the X-ray photons that actually go through the patient and interact with the image receptor are the X-ray photons that are going to penetrate the part and form the image. So now let's talk about beam attenuation. As the primary X-ray beam passes through anatomic tissue, it loses some of its energy. Fewer X-ray photons remain in the beam after it interacts with anatomic tissue, because on the slide before, I was showing you how some are absorbed by the patient, some are scattered, and then some actually interact with the image receptor. This reduction in the energy or number of photons in the primary X-ray beam is known as attenuation. Beam attenuation occurs as a result of the photon interactions with the atomic structures that compose the tissues. So if they are absorbed by the patient's body, they are attenuated. Two distinct processes occur during beam attenuation in the diagnostic range. We have absorption of with the patient's body. So the primary X-ray beam, a portion of it is absorbed by the patient, and then also a portion of it is scattered. So that is beam attenuation. And then what you have left over that did not absorb or scatter is going to create the image for you, which is a very, very small percentage of the primary X-ray beam that comes out of the tube initially. Okay, so here is absorption. As the energy of the primary X-ray beam is deposited within the atoms composing the tissue of your patient, some X-ray photons are completely absorbed. Complete absorption of the incoming X-ray photons occurs when it has enough energy to remove or eject an inner electron shell or an inner shell electron. The ejected electron is called a photoelectron, and this photoelectron is going to quickly lose energy by interacting with the nearby tissues. The ability to remove or eject these electrons, known as ionization, is one of the characteristics of X-ray. In the diagnostic range, this X-ray interaction with matter is known as the photoelectric effect. With the photoelectric effect, the ionized atom has a vacancy, or an electron hole, in its inner shell. An electron from an outer shell is going to drop down and fill that vacancy. Because of the difference in binding energies between the two electron shells, a secondary X-ray photon is now emitted. This secondary X-ray photon typically has very low energy and is therefore unlikely to exit the patient and therefore is absorbed. So the probability of total photon absorption during the photoelectric effect depends on the energy of the incoming X-ray photon and the atomic number of the anatomic tissue. The energy of the incoming X-ray photon must be at least equal to the binding energy of the inner shell electron. After absorption of some of the X-ray photons, the overall energy or quantity of the primary beam is going to decrease as it passes through the patient. So the image over here is the photoelectric effect. So it's showing the incident photon interacting with an inner orbital K or L electron, giving all of its energy to the electron, ejecting it from orbit, and then the photon is absorbed. And then if you look at number 2, this is the ejected electron that was caused by that incident photon. It bumped it out. So that ejected electron is a photoelectron, and its energy is equal to the excess of the electron's binding energy. If you look at number 3, this is where the vacancy is. So this is going to be a vacancy in the inner orbital shell, either K or L, which must be filled. So one of the electrons from the outer orbital shell, usually the next orbit out, is going to drop into that empty space. As the electron drops to that empty space, it may shed its excess energy as a secondary photon. So this is the photoelectric effect. It is the total photon absorption that depends on the energy of the incoming X-ray photon and the atomic number of your patient's part that you are examining, the anatomic tissue. So scattering is when some incoming photons are not absorbed, but instead they lose their energy during the interactions with atoms composing of the tissue. So this process is called scattering, and it results from the diagnostic X-ray interaction with matter known as the Compton effect. The loss of some energy of the incoming photon occurs when it ejects an outer shell electron from a tissue atom. So that ejected electron is called a Compton electron, or we call it a secondary electron. The remaining lower energy X-ray photon changes direction and may leave the anatomic part to interact with the image receptor. In figure 8.3, we can see that the photon interacts with an outer orbital electron, and some of its energy is going to be released from that photon, and then it ejects it from the orbit. So it just bumps it out. So the ejected electron, which is the Compton electron, is going to leave the atom with an energy equal to the excess imparted by the photon. And then the photon continues on an altered path, scattered with less energy than before the collision. Okay, so we're comparing photoelectric and Compton effects. The percentage of photoelectric interactions generally decreases at a higher kV within the diagnostic range. And then the percentage of Compton interactions likely to increase at higher kV within the diagnostic range. Photoelectric effect, we have an incoming photon that has sufficient energy to eject an inner shell electron and become completely absorbed. We have an electron from an outer shell that fills the electron hole or the vacancy. A secondary photon is created because of the difference in the electron's binding energies. The probability of this effect depends on the energy of the incoming X-ray photon and the composition of the patient or the anatomic tissue. Fewer photon interactions occur at higher kV settings, but of those interactions, a smaller percentage are photoelectric interactions. And then with the Compton effect, we have incoming photon loses energy when it ejects an outer shell electron and then changes direction. The scattered photon may be absorbed within the patient. It may leave the anatomic part, or it may interact with the image receptor or expose anyone near the patient because it is scatter. Scattered photons that strike the image receptor provide no useful information. The probability of this effect depends on the energy of incoming X-ray photons, but not on the composition of the anatomic tissue or the patient's part. With Compton effect, there are few photon interactions. There are fewer than the photoelectric effect occurring at the higher kV setting, but of those interactions, a greater percentage are Compton interactions. And a smaller percentage are the photoelectric interactions. Scattered and secondary radiations provide no useful information and must be controlled during radiographic imaging. We have coherent scattering, which is an interaction that occurs with very low energy X-rays, typically below the diagnostic range. So these are very, very low energy X-rays. The incoming photon interacts with the atom, causing it to become excited. The X-ray does not lose energy, but it changes direction. Coherent scattering could occur within the diagnostic range of X-rays and may interact with the image receptor, but is not considered an important interaction in radiography. If a scattered photon strikes the image receptor, it does not contribute any information that we can use to create an image of the anatomic area of interest. If scattered photons are absorbed within the anatomic tissue of your patient, they contribute to the radiation exposure to your patient. In addition, if the scattered photon leaves the patient and does not strike the image receptor, it could contribute to the radiation exposure of anyone near the patient as well, including yourself, including the RT. Transmission is when the incoming X-ray photon passes through the anatomic part without any interaction with the atomic structures. The combination of absorption and transmission of the X-ray beam is going to provide an image that structurally represents the anatomic part being imaged. Because scatter radiation is also a process that occurs during interaction of the X-ray beam and the anatomic part being imaged, the quality of the image created is compromised if the scatter photon strikes the image receptor. So you can see here in this picture showing transmission, the X-ray photons are passing through the patient without any interaction with the anatomic structures. And then they are directly hitting the image receptor. The amount of X-ray beam attenuation is affected by the thickness of the anatomic part, the tissue atomic number and tissue density, and the energy of the X-ray beam going through it. For a given anatomic tissue, increasing its thickness increases the beam attenuation by either absorption or scattering. So in figure A, you can see the transmission occurring. That's where the X-ray photons are going through the anatomic part without any interaction to that anatomic part, and they are hitting the image receptor. In figure B, you can see that the X-ray photons are being absorbed by the anatomic part. 2 out of 4 in this picture are hitting the image receptor. The other 2 are being absorbed by the part. So that is beam attenuation, and it's due to the tissue thickness. So there's factors affecting beam attenuation. X-rays are attenuated exponentially and generally reduced by approximately 50% for each 4 to 5 centimeters of tissue thickness. The thicker the anatomic part, the more X-rays are needed to produce the radiographic image. The thinner the anatomic part, the fewer X-rays are needed to produce a radiographic image. And you will control this at the control panel by changing your technique. In figure 8.6, you can see that this is tissue beam attenuation. X-rays are attenuated exponentially and generally reduced by the 50% for 4 to 5 centimeters of tissue. So in this picture, you can see these are 100 X-ray incidents, number of X-rays at the beginning of each centimeter of tissue interval, and then this is about 5 centimeters of tissue. So you can see it's going to change. So 100 X-ray incidents going into the tissue. It's going to decrease at the top layer to 50 X-rays. And then on the bottom layer is 5 centimeters of tissue. So that's going to attenuate and take the 100 X-rays down to 25. So exiting that tissue is going to be even less. So if we're giving the patient 100 X-rays, right, there's going to be less than 25 that actually interact with the image receptor to create the initial image or the latent image. Tissue composed of a higher atomic number, such as bone, attenuates the X-ray beam more than tissue composed of a lower atomic number, such as fat. The higher atomic number indicates there are more atomic particles for interaction with the X-ray photons. X-ray absorption is more likely to occur in tissues composed of a higher atomic number when compared with tissues of a lower atomic number. Tissues that absorb more X-rays demonstrate increased brightness. That's going to be displayed in the digital image. Tissues that transmit more X-rays absorb fewer X-rays, demonstrate decreased brightness displayed in the digital image. In figure 8.7 here, you can see that bone absorbs more radiation than fat or air. You can see the X-ray photons going in, and here's the bone, and so only one is coming out. So that means that the majority was absorbed by the bone. Fat, a little bit fewer are absorbed by fat, so we have more X-rays interacting with the image receptor. Air, nothing is absorbed, and they all are going to interact with the image receptor. Another factor that affects the beam attenuation is tissue density. Matter per unit volume, or the compactness of the atomic particles composing the anatomic part, also affects the amount of beam attenuation. For example, muscle and fat tissue are similar in composition. Their atomic particles differ in compactness, and therefore the tissue density varies. With muscle tissue, it has atomic particles that are more dense or compact, and therefore attenuate the X-ray beam more than fat cells. Bone is composed of tissue with a higher atomic number, and the atomic particles are more compacted or dense. Anatomic tissues are typically ranked based on their attenuation properties. There are 4 substances that account for most of the beam attenuation in the human body: bone, muscle, fat, and air. Bone attenuates the X-ray beam more than muscle. Muscle attenuates the X-ray beam more than fat. Fat attenuates the X-ray beam more than air. And the atomic number of the anatomic part and its tissue density affect X-ray beam attenuation. So to remember from the slide before, bone, muscle, fat, air, to remember them in order, I always remember bring me fat apples. All right, so I'm talking about X-ray beam quality. So the quality of the X-ray beam or its penetrating ability is going to affect its interaction with anatomic tissue. Higher penetrating X-rays, which is the shorter wavelength with higher frequency, are more likely to be transmitted through anatomic tissue without interacting with the tissue's atomic structures. Lower penetrating X-rays, which are longer wavelength and low energy or low frequency, are more likely to interact with the atomic tissues or atomic structures and be absorbed. The kV selected during X-ray production is going to determine the energy or the penetrability of the X-ray photon, and this is going to affect its attenuation in the anatomic tissues. Beam attenuation is decreased with a higher energy X-ray beam and increased with a lower energy X-ray beam. So looking at this image here, we can see 2 different interactions. So the one to the left is going to be an interaction with low kV, so low energy X-ray beam. And you can see that X-ray photons are coming in to the anatomic structure, and most X-ray photons are going to be absorbed by the patient, and few are going to strike the image receptor. On the other one, you see a high energy X-ray beam. So this is high kV. The X-ray photons are going in, and photons have more energy to penetrate the part, so they're not being absorbed. They're just going right through. So there are more X-ray photons interacting with the image receptor. So your kV is your penetrability. So with higher kV, you're able to penetrate the part, and it doesn't just sit around and become absorbed inside the patient. It penetrates and goes all the way through to the image receptor. All right, this chart will show what goes on with a beam attenuation, the absorption, and the transmission, depending on different factors. So we have tissue thickness. So the increasing thickness of the tissue is going to cause the beam attenuation to increase. Absorption will increase. So if we have the beam being attenuated and the X-ray photons being absorbed by the patient's body, then the transmission, which is the X-ray photons going down and interacting with the image receptor, are decreased. If we have decreasing thickness, then that means there is decreased beam attenuation, decreased absorption. So of course, this will allow the X-ray photons to go straight through the patient and interact with the image receptor. So you have an increased transmission. If we're looking at the atomic number of the tissue, the increasing atomic number of the tissue, beam attenuation will increase, absorption will increase, transmission decrease. Decreasing atomic number will be the opposite. So we have a decrease in beam attenuation, decrease in absorption. So that means that more X-ray photons are going to interact with the image receptor. So you have an increased transmission. Tissue density, increasing the tissue density. It's going to increase beam attenuation. There's more tissue for the beam to be absorbed in, right? So your absorption will be increased. And then, of course, the transmission will be decreased because more is being attenuated, more is being absorbed, so less are going to make it to the image receptor. The decreasing tissue density, you have a decreased beam attenuation, decreased absorption, and more X-ray photons are interacting with the image receptor, so you have an increased transmission. X-ray beam quality, increasing the beam quality. Beam attenuation is decreased. Absorption is decreased. Transmission is increased. Decreasing the beam quality. Attenuation is going to be increased. Absorption's increased. Transmission is decreased. The imaging effect. When the attenuated X-ray beam leaves the patient, the remaining X-ray beam, referred to as exit radiation or remnant radiation, is composed of both transmitted and scattered radiation. The varying amounts of transmitted and absorbed radiation, or differential absorption, create an image that structurally represents the anatomic area of interest. Scatter exit radiation, which is a Compton interaction that reaches the image receptor, does not provide any diagnostic information about the patient. Scatter radiation creates unwanted exposure on the image, and this is called fog or image fog. Methods used to decrease the amount of scatter radiation reaching the image receptor we will discuss later on in the chapter. When you look at figure 8-9 here, when the attenuated X-ray beam leaves the patient, the remnant X-ray beam is composed of both transmitted and scattered radiation. So you have your primary radiation coming into the patient. Some of it, of course, will be absorbed. Some of it will be scattered. And then some of it will be transmitted, which is the transmission, the X-ray photons that actually meet the image receptor and interact with the image receptor to create the image. If you look here at the image of the KUB, the areas within the anatomic tissue that absorb the incoming X-ray photons, which is called the photoelectric effect, are going to create the white or clear areas, which is increased brightness on the image. The incoming X-ray photons that are transmitted create the black areas, which is the decreased brightness on the image. And then anatomic tissues that vary in absorption and transmission are going to create a range of dark and light areas, which are your shades of gray. The various shades of gray or brightness recorded in the image make anatomic tissue visible. Skeletal bones are differentiated from the air-filled lungs because of their differences in the absorption and the transmission. Anatomic tissues are going to vary in their absorption and transmission of the X-ray photons, and they're going to create that brightness and absorption areas. So you can see the bone is showing up increased brightness. You have your shades of gray out here. And then air will show up black, so you have a decreased brightness. Fluid will also show up white. So if you have a chest x-ray, you're looking at the black air in the lungs, but then you see a little bit of white in there. That's either going to be fluid in the lungs, or also it can be the pulmonary vessels, because the pulmonary vessels are going to have blood in them. So blood will show up as white as well. With image receptors, less than 5% of the primary beam interacting with the anatomic part actually reaches the image receptor, and an even lower percentage is used to create the image. The exit or remnant radiation leaving the patient interacts with the image receptor to create the latent or invisible image. The latent image is not visible until processed to produce the manifest or visible image. There are two types of image receptors, and they're used in radiography, which are digital and film screen. We don't see film screen much anymore at any of the clinical sites. You're mainly going to be using computed radiography and digital radiography. Digital imaging can be accomplished by using a specialized image receptor that acquires the latent image, and then the computer processes the visible image for display on the monitor. This image receptor is called an array, ARRAY. There are several types of digital image receptors used in diagnostic imaging. Unlike the film screen imaging, in which the film is the medium to acquire, process, and display the image, digital imaging includes 3 separate stages. The digital image receptor acquires the latent image, the computer processes the image, and then the monitor displays the visible image. So like I said before, film screen imaging is pretty much obsolete, but it's still important to know about it. So film screen imaging uses a cassette or a light, tight container for the radiographic film. The film is placed between 2 intensifying screens within the cassette. The exit radiation interacts with the intensifying screens, and it is converted to visible light. So that's where you're going to have that fluorescence going on and the glowing inside of the cassette. The intensifying screens serve to intensify the action of the x-rays. It's going to reduce the radiation exposure to the patient. And because x-rays have more energy than visible light, fewer x-rays can be used to image the area of interest when using an intensifying screen. The visible light energies emitted from the intensifying screens are proportional in quantity or intensity to the radiation exiting the patient. The film records the latent image based on the pattern of the remnant x-rays and the light produced by the intensifying screens. Then the absorption of visible light by the film's emulsion initiates a conversion process that is continued by chemical processing to create a permanent visible image, which is the manifest image. The composition and type of film and intensifying screens, in addition to the quality of film processing, have an important role in radiographic imaging. Both digital and film screen radiography creates a static image of the anatomic area of interest. Dynamic imaging or fluoroscopy is going to provide imaging of the movement of the internal structures. Fluoroscopy or fluoro differs from static imaging by its use of a continuous beam of x-rays to create images of moving internal structures that can be viewed on a display monitor. So fluoro is dynamic, not static. Internal structures such as the vascular or the GI systems can be visualized in their normal state of motion with the aid of a contrast media, either liquid or gas. And we can either inject or have the patient drink, or we can do an enema for like a barium enema. Although there are newer digital technologies available for fluoro, the basics of image intensified fluoro are still important and need to be understood. So during image intensified fluoro, the internal structures can be best visualized when the images are brighter. Creating a brighter image is accomplished with image intensification. Image intensification is the process by which the exit radiation from the anatomic area of interest interacts with a light emitting material, which is the IP or the input phosphor, for the conversion to visible light. The light intensities or energies are equal to the intensities of the exit radiation and are converted to electrons by a photocathode, which is called photoemission. The electrons are then focused by electrostatic focusing lenses and then accelerated toward the anode to strike the output phosphor and create a brighter image. And you can see all of this in the figure 8-12. These are all the major components of the image intensifier. So we have the output phosphor at the top here. You have your anode, the focal point, the electrostatic lenses, the electrons, the photocathode, and the input phosphor, and then the glass envelope encircles all of this. Brightness gain. So a brighter image is a result of the high energy electrons striking the small output phosphor. Accelerating these electrons increases the light intensities at the output phosphor, and this is called the flux gain. The reduction in size of the output phosphor image as compared with the input phosphor image also increases the light intensities. This is called the minification gain. The brightness gain is the product of both flux gain and minification gain, and it results in a brighter image on the output phosphor. Although the term brightness gain continues to be used throughout this chapter, it is now common practice to express the increase in brightness with the term conversion factor. The conversion factor is an expression of the luminance at the output phosphor divided by the input exposure rate. The image light intensities from the output phosphor are converted to an electronic video signal and then sent to a display monitor for viewing. Additional filming devices such as a spot film or cine, which is a movie film, can be attached to the fluoro system to create permanent radiographic images of specific areas of interest. Additionally, the electronic video signal created from the output phosphor light intensities during image intensified fluoro can be converted to digital data and displayed on a high resolution display monitor. Once the fluoro image is digitized, a computer can manipulate the image in a variety of ways. You guys will see fluoro discussed more in detail in chapter 14. But whether the radiographic image is displayed on a computer monitor or on film, the process of differential absorption for image formation remains the same. The varying X-ray intensities exiting the anatomic area of interest form the image. And then in chapter 14, there will be further discussion of radiographic image characteristics, exposure technique selection, image receptors, the control of scatter radiation, and then problem solving, all in chapter 14. So we'll talk about this a little bit more later, but that is the end of this chapter.